Hello, everyone. Hopefully you're having a good day. Today we'll be going over workshop 2, option 1. So I will go ahead and share my screen so we can get this lesson started. Okay. So for option 1, we have language L1, which is X such that X contains an equal number of zeros, ones, and twos. We can also represent this in another way, where language L1 is equal to 0 to the n, 1 to the n, 2 to the n, such that n is greater than or equal to 0. We will show that this is not context-free. Before we can do that, we must assume that L1 is context-free, so we can use the context-free or the pumping lemma for context-free languages and use contradiction to prove that it is not a context-free language. L1 may have a pumping length P. So we'll take a string S such that the length of S is greater than or equal to P, the pumping length. We will divide S into 5 parts, U, V, X, Y, and Z. And the pumping lemma for context-free languages has these 3 cases. For each I greater than or equal to 0, we have U, V to the I, X, Y to the I, Z is in L1. So what this means is that if we raise V and Y to any I, we will still have the same amount of zeros, ones, and twos in L1. Second case, we have the length of Vy is greater than 0. And third, we have the length of the xy is less than or equal to the pumping length P. So first, let us try and prove the first case, which is, to reiterate, for each I greater than or equal to 0, U, V to the I, X, Y to the I, Z is in L1. So let's take our pumping length P and our string and raise each 0, 1, and 2 to our pumping length P. So for example, if our pumping length P is 4, our string will have 4 zeros, 4 ones, and 4 twos. And then our string will be as such. And if we divide S into U, V, X, Y, and Z, and V and Y can only contain one symbol, so we will have to divide it as such. This is one way that you can divide it with U as 1 0, V as 2 zeros, and X has a 0, 4 ones, a 2, and Y has 1 2, Z has 2 twos. So just as a refresher from last slide, here's how we divided up our string. And then if we go back to the first case, U, V to the I, X, Y to the I, Z, and we set I equal to 3, here is what will happen. We'll still have 1 0 for U, but for V, we will have 3 times 2, because in V, to start off with, we have 2 0. And then we will end up with I equal to 3, we'll end up having 6 zeros. X will remain the same. And in Y with I equals 3, we will have 3 twos rather than 1. And then for Z, we'll have the same, which is 2 twos. So if we go ahead and count up the amount of zeros, ones, and twos in our new string, we find out that we now have 8 zeros, 4 ones, and 6 twos. So this is not in L1 because if we recall, L1 is equal to 0 to the n, 1 to the n, 2 to the n, which means that there should be the same amount of zeros, ones, and twos. And when we look at the first case, there is not an even number of ones, twos, and zeros any longer. So since this does not pass the first case, we have proven that L1 is not a context-free language. Therefore, we'll not have to go into the other cases. We have already proven that it's not a context-free language. So next, we will look at how this language can be decided using a deterministic Turing machine. So this machine I have created in using JFlap, and I will run you through the basics on how it works. So first of all, just recall we have zeros, ones, and twos. So at the beginning of the tape, on input of a 0, the machine will put down an X, and then move the tape over to the right. And then once we get here, if the machine sees another 0, it'll just put down the 0, just keep the 0, and move the tape to the right until, and I'll keep doing that until we reach a 1, which at this point, it'll put down a Y, move the tape to the right. It'll keep walking over the ones, keep moving the tape to the right until we reach a 2. And then at that point, it'll put down a Z. And then here, it'll walk the tape back to the left. And then we will keep walking back to the left across the Z's, the ones, the zeros, and the Y's until all the way until we reach our X. And so at this point, it depends on what the next input is, but if there is another 0, then it will put a X down again. Then it will look for more zeros and any Y's, and then it'll continue moving over those, moving the tape to the right until we reach another 1 where it'll put a Y down. And then it'll come over here, move it to the right, keep looping, moving to the right over ones and Z's until we reach another 2. And then at that point, it'll go back to the left and then loop back to the left, walk back over the Y's, the zeros, ones, and Z's until we reach an X again. So we'll keep doing this until there is no longer a 0 once it moves to the right from X. So at this point, that there are even number of zeros, ones, and twos. Once we reach this point, we should, upon moving to the right, we should run into a Y. And then once that happens, that means that we have already gone over all the zeros, turn those into X's, and we should also have an even number of Y's and Z's. So what this will do is if we have, once we have reached a Y, it'll move the tape to the right. And then once it does that, it'll keep moving to the right over all the Y's. And then once it gets to the Z's, it'll keep moving to the right all the way to the end until we have reached our empty string. And then at this point, we can go to our except state. As you notice here, however, let's just go back. If you look at L1, we have an even number of zeros, ones, and twos, such that n is greater than or equal to 0. So if we have a 0 just right away, if we have an empty string right off the bat, we can also go to our except state. So that was just a recap, how we proved that this language L1 is not context-free, and then how we could build a deterministic Turing machine to decide that language. I hope you enjoyed this lesson and have a great day.